Welcome to the session on theory of equations. The theory of equations is the study of algebraic equations, also called polynomial equations, which are equations defined by a polynomial. The branch of mathematics concerned with the finding facts concerning the roots of algebraic equations and finding methods for obtaining them. An expression of the form f of x is equal to a naught x raised to n plus a1 into x raised to n minus 1 plus etc. plus a n minus 1 into x plus a n, where a naught, a1, etc., a n are constants and n is a positive integer. Here these are constants, a naught, a1, a2, etc., a n minus 1, a n, all are constants, and n is a positive integer. This is called a polynomial in x of degree n. Here note that a naught should be not equal to 0. The equation f of x equal to 0, that is a naught x raised to n plus a1 x raised to n minus 1 plus etc. plus a n equal to 0. This equation is called a polynomial equation or an algebraic equation of nth degree. Here also a naught should be not equal to 0. Alpha is said to be a root of the equation f of x equal to 0. Alpha is said to be a root of this equation f of x equal to 0 if f of alpha is equal to 0. If alpha is a root of the equation f of x equal to 0, then x minus alpha is a factor of f of x, which is known as the factor theorem. The theory of equations is developed on the basis of the following two fundamental theorems. First one is, every equation has a root which may be real or imaginary. Every equation has a root which may be real or imaginary. And the second one is, every polynomial equation of nth degree has n and only n roots. A polynomial equation of nth degree has n and only n roots. These are the two fundamental theorems. On the basis of these two fundamental theorems, we will discuss the theory of equations. Let the equation be f of x is equal to 0. We take the equation as f of x is equal to 0. Then by the fundamental theorem, this has a root, say alpha 1. Alpha 1 is a root. That is, we can write f of alpha 1 is equal to 0. If alpha 1 is a root, means the equation will satisfy x is equal to alpha 1. Therefore, we can write f of alpha 1 is equal to 0. Therefore, we can say that x minus alpha 1 is a factor of f of x. That is, f of x can be expressed as f of x is equal to x minus alpha 1 into some function of x, let it be phi 1 of x, where phi 1 of x is an algebraic polynomial of degree n minus 1. Now, consider the equation phi 1 of x is equal to 0. Obviously, this equation has a root, say alpha 2. Therefore, we can write phi 1 of alpha 2 is equal to 0, and hence x minus alpha 2 is a factor of phi 1 of x. X minus alpha 2 is a factor of phi 1 of x. Therefore, phi 1 of x can be written as x minus alpha 2 into some function of x, say phi 2, where phi 2 of x is a polynomial of degree n minus 2. Phi 2 of x is a polynomial of degree n minus 2. Therefore, we can write f of x as f of x is equal to x minus alpha 1 into phi 1 of x, where phi 1 of x is x minus alpha 2 into phi 2 of x. That is, f of x is equal to x minus alpha 1 into x minus alpha 2 into phi 2 of x. By continuing this process, we can write f of x as f of x is equal to x minus alpha 1 into x minus alpha 2 into x minus alpha 3 into etc. x minus alpha n into phi n of x, where phi n of x is a polynomial of degree n minus n, that is 0. Phi n of x is a polynomial of degree 0. That is, phi n of x is a constant only. Therefore, we can write f of x as x minus alpha 1 into x minus alpha 2 into etc. into x minus alpha n into phi n of x is a constant. We denote that constant by a naught. Therefore, f of x is equal to a naught into x minus alpha 1 into x minus alpha 2 into etc. into x minus alpha n. Hence, f of x is equal to 0 has n roots alpha 1, alpha 2 etc. alpha n. Since f of x not equal to 0 for any other value of x except alpha 1, comma alpha 2, comma etc., comma alpha n, the equation has only n roots. Of course, this may be real, complex, or may be distinct or equal. If f of x is equal to 0 is a polynomial equation, and if f of a and f of b are of opposite signs, f of a and f of b are of opposite signs, then at least one root of the equation f of x equal to 0 must lie between a and b, because f of a and f of b are of opposite signs, means f of a may be here, where f of b may be here. Therefore, this graph will touch the x axis at one point, obviously, at least one point. Using the above theorem, we can show that if f of x is equal to 0 is an equation of odd degree, then it has at least one real root whose sign is opposite to that of the last term. If f of x is equal to 0 is of even degree and the constant term is negative, the equation has at least one positive root and at least one negative root. And if f of x equal to 0 has no real root between a and b such that a is less than b, then f of a and f of b are of same sign. Now, I shall introduce few theorems which will be useful in solving certain equations. First one is, in a polynomial equation with real coefficients, imaginary roots occur in conjugate pairs. That is, if alpha plus I beta is a root of the equation, then alpha minus I beta is also a root of the same equation f of x equal to 0. That is, the imaginary roots occur in conjugate pairs. Consider the proof of this theorem. Alpha plus I beta where beta not equal to 0 and alpha and beta are real, be a root of the equation f of x equal to 0, means f of alpha plus I beta is equal to 0. Alpha, if alpha minus I beta is again a root of the equation, we can say that f of alpha minus I beta, which is also equal to 0. Now consider this term x minus alpha plus I beta. Alpha plus I beta is a root, means we can write the factor as x minus alpha plus I beta. If alpha minus I beta is also a root, then we can write the corresponding factor x minus of alpha minus I beta. Now consider this product of the two factors, that is x minus of alpha plus I beta into x minus of alpha minus I beta, which can be written as from here we can write x minus alpha minus I beta into, from this we can write x minus alpha minus of minus I beta means plus I beta. This is of the form a minus b into a plus b, that is a square minus b square. Therefore, we can write this equal to x minus alpha the whole square plus I beta the whole square, that is I square beta square, not plus, it is minus I beta the whole square, that is I square beta square. I square means minus 1, therefore minus of minus will become plus beta square. When f of x is divided by x minus alpha whole square plus beta square, let the quotient be phi of x and remainder be ax plus b. Consider the quotient as phi of x and remainder as ax plus b. When we divide f of x by x minus alpha whole square plus beta square, therefore f of x can be written as f of x is equal to x minus alpha the whole square plus beta square, this into phi of x plus ax plus b, this into phi of x plus the remainder ax plus b. Since f of alpha plus I beta is equal to 0, we get a of alpha plus I beta plus beta is equal to 0. F of alpha plus I beta equal to 0, we put x is equal to alpha plus I beta, we will get the left hand side as f of alpha plus I beta is equal to here alpha plus I beta minus alpha the whole square plus b square into phi of alpha plus I beta plus a into alpha plus I beta plus b. f of alpha plus I beta is 0. This is alpha minus alpha, that is 0. Here I beta whole square, that is minus beta square, plus beta square means 0. Therefore, 0 into phi of alpha plus I beta means 0, plus here a of alpha plus I beta plus b, b. That is a of alpha plus I beta plus b is equal to 0. That is a alpha plus beta, a alpha plus b, not beta, b, a alpha plus beta plus a into I beta. Is equal to 0. This means that, consider this a alpha plus b as a single term. This sum equal to 0 means both these two terms will be 0. That is a alpha plus b equal to 0, and here I not equal to 0 means a into beta is equal to 0. Beta not equal to 0 implies that beta does not equal to, beta should not be equal to 0, which means that from this we can write a equal to 0. And hence, when a equal to 0, from this equation we can write b is equal to 0. Therefore, f of x can be written as f of x is equal to x minus alpha the whole square plus beta square plus phi, this into phi of x. This is our f of x. Here a and b are 0 means this term will become 0. Therefore, f of x equal to x minus alpha the whole square plus beta square into phi of x. F of alpha minus I beta equal to, we can write from here alpha minus I beta minus alpha the whole square plus beta square into phi of alpha minus I beta, which is equal to 0. Therefore, alpha minus I beta is also a root of the equation f of x equal to 0. From this we can say that alpha minus I beta is a root of the same equation f of x is equal to 0. That is, if alpha plus I beta is a root of the equation, then obviously alpha minus I beta is the root of same equation f of x equal to 0. Now consider one example. Solve the equation x raised to 4 plus 4x cube plus 5x square plus 2x minus 2 is equal to 0. Given that minus 1 plus I is a root, we are given that minus 1 plus I is a root of this equation, then find the solution of the corresponding differential equation. This is the corresponding polynomial equation. This is of degree 4. Therefore, this equation has 4 roots. One root is minus 1 plus I. From the above theorem, we can say that if minus 1 plus I is a root, therefore, obviously minus 1 minus I is also a root. Now consider this product x minus 1 plus I, that is minus 1 plus I is a root, means we can write x minus of minus 1 plus I is a factor. Similarly, minus 1 minus I is again a root, means we can write the factor as x minus 1 minus I. Product of these two factors is equal to, from here we can write x plus 1 the whole square plus 1 square, that is 1, which is equal to x square plus 2x plus 2. Now, when the polynomial is divided by x square plus 2x plus 2, the remainder will become 0. Therefore, we can write x raised to 4 plus 4x cube plus 5x square plus 2x minus 2, which is equal to x square plus 2x plus 2 into some function of x, let it be x square plus lambda x minus 1. Equating coefficient of x cube on both sides, we will get here the coefficient of x cube is x square into lambda x, means the coefficient is lambda. In this term, 2x into x square will become 2x cube, therefore, in which case the coefficient is 2. Therefore, the coefficient of x cube in the right hand side is lambda plus 2, which is equal to, in the left hand side the coefficient of x cube is 4. From this we can write lambda is equal to 4 minus 2, that is lambda is equal to 2. Therefore, f of x can be written as x square plus 2x plus 2 into x square plus lambda x, lambda is 2, therefore 2x minus 1. Solving x square plus 2x minus 1 is equal to 0. We will get x as minus 2 plus or minus root of 8 divided by 2 by the quadratic form. We can obtain, we will obtain x is equal to minus 2 plus or minus root 8 divided by 2, which is equal to minus 1 plus or minus root 2, because root 8 is 2 root 2. When we divide by 2, we can write x as x is equal to minus 1 plus or minus root 2. Therefore, the roots are the roots of given equation are, first root is minus 1 plus I, it is given. From the above theorem, we say that minus 1 minus I, that is the conjugate of the given complex root. Therefore, minus 1 plus I comma minus 1 minus I. From here, we obtained two roots, minus 1 plus root 2 and minus 1 minus root 2. These are the four roots of the given equation. The second theorem is in a polynomial equation with rational coefficients, the irrational roots in the form of quadratic surds occur in conjugate pairs. That is, if a plus root b is a root of the equation f of x equal to 0, then a minus root b is also a root of the same equation f of x equal to 0. Let a plus root b be a root of the equation f of x equal to 0, where b not equal to 0. Here b should not be equal to 0, and b is not a perfect square. This b is not a perfect square. A and B are rational numbers. A and B are rationals. Now, A plus root B is a root of the equation f of x equal to 0, means we can write the factor as x minus of A plus root B. And we claim that A minus root B is also a root of the same equation f of x equal to 0. Therefore, we can write the factor as x minus of A minus root B. Now, consider product of these two factors. This can be written as, from here, x minus A plus root B into x minus A minus root B. X minus A plus root B, here minus root B. This is not plus, here minus. In this term, it is root B, which is equal to x minus A square minus root B whole square, that is B. Therefore, when f of x is divided by x minus A the whole square minus B, let the quotient be phi of x and the remainder be Ax plus B. Consider the quotient as phi of x and the remainder as Ax plus B. When we divide the function f of x by this factor x minus A the whole square minus B, therefore, f of x can be written as f of x is equal to x minus A the whole square minus B, this into phi of x plus the remainder Ax plus B. Now, f of A plus root B is a root of the equation f of x equal to 0, means f of A plus root B is equal to 0, which implies that A of A plus root B plus B is equal to 0. When we substitute x is equal to A plus root B in this expression, we will obtain A of A plus root B plus B is equal to, from here we will get phi of x into 0, that means 0. That is A into A plus root B plus B is equal to 0. Equating the rational and irrational parts, we will get A into A plus B is equal to 0 and A into root B is equal to 0. A into root B is equal to 0. Since B not equal to 0, from this we can write A is equal to 0. Therefore, from here A equal to 0 means B also is equal to 0. Therefore, we can write f of x as f of x is equal to x minus A the whole square minus B into phi of x. Therefore, f of A minus root B can be written as A minus root B minus A the whole square minus B into phi of A minus root B. This will become equal to 0. Hence, we can conclude that A minus root B is also a root of the equation f of x is equal to 0. That is, if A plus root B is a root of the equation f of x equal to 0, then obviously a minus root b is again a root of the same equation, f of x is equal to 0. Now consider this example. Solve the equation x raised to 4 plus 2x cube minus 16x square minus 22x plus 7 is equal to 0, given that 2 plus root 3 is a root. From the previous theorem, we can say that if 2 plus root 3 is a root, then 2 minus root 3 is also a root of the same equation, f of x equal to 0. Therefore, the factor of f of x corresponding to these two roots is equal to x minus 2 plus root 3 into x minus 2 minus root 3. This is the corresponding factor, which is equal to, from this we can write this equal to x minus 2 whole square plus root 3 whole square, that is plus 3. Not here plus 3, it is minus, because from here we can write x minus 2 minus root 3 into x minus 2 plus root 3, which is of the form a minus b into a plus b, that is a square minus b square. Therefore, we can write x minus 2 whole square minus 3, which is equal to, on expanding, we will get x square minus 4x plus 1. Now, let f of x is equal to this left hand side, that is x raised to 4 plus 2x cube minus 16x square minus 22x plus 7, which is equal to x square minus 4x plus 1 into x square plus lambda x plus 7. Now, equating the coefficients of x on both sides, we will get lambda minus 28 is equal to minus 22, because in the left hand side the coefficient of x is minus 22. From here the coefficients of x are lambda x into 1, that is lambda, 7 into minus 4x, that is minus 28x, therefore coefficient of x is minus 28. Therefore, we can write lambda minus 28 is equal to minus 22. This implies lambda is equal to 6. Therefore, f of x can be written as x square minus 4x plus 1 into x square plus 6x plus 7. The remaining two roots are given by solving x square plus 6x plus 7 is equal to 0. By solving this equation, we will get the remaining two roots. On solving, we will get x as minus 3 plus or minus root 2 by quadratic form. Therefore, the roots are given by 2 plus root 3, obviously 2 minus root 3, and from solving these two equations, this equation, we will get the remaining two roots as minus 3 plus root 2 and minus 3 minus root 2. These are the 4 roots of the given equations. With this example, let me conclude this session. Thank you for listening the class. Have a nice day.